Well, hello. Welcome to WSQ number 16. I'm Mr. Filburn, of course. And today we're going to talk about probability and heredity. Three objectives for us today as we continue to talk in our journey of genetics. We want to learn what is probability and how does it help explain the results of genetic crosses. We're going to learn what is meant by the terms genotype and phenotype. And we're going to learn about something known as codominance. So that's what we've got on the docket today, so let's get started. First of all, let's discuss what probability is. Probability is a mathematical term, and it actually is a number that describes how likely it is that a certain event will occur. So we're talking about probability, we're talking about the likeliness. Okay, now that means that the law of probability can only predict what is likely or expected to occur, not necessarily what will actually occur. I'll give you an example from the natural world. Let's say you are tossing a coin. Now, if I have a quarter, that quarter has two things on it. It's got a head on one side, it's got a tail on the other side. Those are the only options. So as I flip that coin in the air and allow it to drop onto the table, there's only two choices. It's going to land heads or it's going to land tails. Okay? The probability or the likelihood that it lands heads is 1 out of every 2 flips, right? There's only 2 choices. So as it goes up, I have a 50% chance that it's going to land heads and a 50% chance it's going to land tails. Now, does that mean that every other time it will just go heads, tails, heads, tails, heads, tails? Of course not. We know that's not what happens in real life. It may land heads 50 times in a row. Does that change the probability that it will land tails? It doesn't. And so that's really important when we talk about statistics. A dice is another example, a 6-sided dice like the image below. That dice, I can roll it. It's going to have a 1 in 6 probability of landing a 1, a 2, a 3, a 4, a 5, or a 6. That probability is not going to change no matter how often I roll it, as long as the dice is actually legal and not weighted. So that's what probability is talking about. And probability is connected to genetics because, see, here's the key. What we're going to talk about today is, let's say we've got over here, we're going to talk about the genetics of dad. Okay, ooh, he's got a weird eye there. Okay, and the genetics of, sorry, ladies, the genetics of mom. Okay, now when those genetics combine into baby, it's got a weird nose, okay, and a really weird eye. There we go. There is a probability of certain traits getting passed down from dad and from mom to baby. That probability is important to understand, and it's basically just we're dealing with math. It's just genetical probability, and so that's probably the number that describes how likely it is a certain event will occur. Now, to understand probability, we have to be able to understand how to work with percentages. Probability oftentimes will be expressed as a percentage. So that means that a percentage is taking a number and comparing it to 100. When 100% meaning everything, right? If you say 50%, that means 50 out of 100 events. So if I flipped that coin and I landed heads 50 out of 100 flips, tails 50 out of 100 flips, the percentage probability of landing heads would be 50%. So let's take an example. Let's say you had 3 of 5 coin toss that landed with a heads up. Here's how you can actually calculate it. You would actually write the comparison as a fraction, so 3 out of 5, and then you would multiply that fraction by 100 over 1. And so that would give us 300 over 5. 300 divided by 5 would equal 60. And you're going to make sure that's 100% over 1, right? So that's how we do it. Let's do an example. I want you to write this one down and solve it in your notebook. So let's suppose you take 3 out of 12 coins landed tails up. How can you express this as a percent? So remember, first thing we need to do is we need to write it as a fraction. So 3 out of 12. Second thing we need to do is we need to multiply by 100% over 1. So our answer to this would be 300 over 12. If you know how to divide, well, 300 divided by 12 would give us the answer of 25%, right? So that would mean if I'm getting 3 out of every 12 coins, that's a 25% probability rate. Really important that you understand that concept as we go forward, that you can actually talk about probability and make sense with it, okay? If you can't, please do that. All right. So let's continue on Punnett squares. So with probability in the back of our mind, it's now important to understand what's this look like in genetics. So we're going to take the example of a Punnett square. Punnett's it's named after a scientist in the 1900s who came up with this methodology of genetics and understanding the way that things were aligned. The diagrams of a Punnett square are just basically making a square and being able to take the alleles of the genotypes of an organism and then their mate and crossing those and determining what's the probability of their offspring. So we're going to use an example from Mendel, who dealt with pea plants, and one of the traits he looked at was the seed shape of the pea plants that were coming out. And so what we're going to do is we're going to use this diagram above and this information. We're going to take a cross, and in our cross both parents are heterozygous. Remember, heterozygous, it's a term we haven't got into, but that means that they have different alleles. It's basically they're hybrid. And so they're heterozygous for the trait of seed shape. Okay? R, big R, capital R, is our dominant allele, and it's going to be round. So these are our round dominant trait. And lowercase r, our recessive trait, is going to be our wrinkled. So this is lower r. Okay? This is our recessive or wrinkled allele. So the first thing we're going to do is we're going to, and I want you to draw this in your notes, we're going to draw a square. So we're going to draw a box, and we're going to draw two lines inside of it to divide it into 4 equal spots. Okay, basically, we're looking at probability. Secondly, then what I want you to do is we're going to write the male parents, so we'd have the male parents information along the top of the square, and the female parents alleles along the left side. So now we've got males. Okay, in this case, now how do we know it's big R, little r, big R, little r? Is because remember we said they were heterozygous, meaning different alleles. Okay, so that's our first step, draw. Second step, go ahead and put the alleles of the parent. The third step then is we're going to actually just copy the female parent's alleles into the boxes to their right. Okay, so I'm going to take these, and I have a big R and a big R. They all just kind of come across the line, and then I have a little r and a little r. Okay, and then we're going to do the same thing with the male one, right? So with the male one, let me erase my, there we go. So then what I do is do the same thing with the male. So I have the big R coming from this one and the big R coming from here. You'll see the same pattern. And then the little r going into this box and the little r going into this box. You're just tracking it down and across. And that gives us the completed Punnett square. And this shows all the possible combinations of offspring. So from 2 heterozygous offspring, they can have basically a couple different things. They have a 1 in 4 chance of having big R, big R. That would be a purebred or homozygous. And in this case, those would be R, remember we said, are the round. So that'd be a purebred round-seeded offspring. They have a 25% of having little r, that would be a purebred, and that would be not round, but that would be lowercase r, wrinkled, right? Or they have a 50%, because they have RR and RR, which are the same, a 50% probability of getting a, just like them, a heterozygous, okay, round, so it would be heterozygous, which would be like hybrid, round seed pods or pod shape, seed shape. So with that being said, they have ultimately a 75%, see 3 out of 4 squares, of having round seeds, 25% chance of having wrinkled seeds. That's how Punnett squares work. Punnett squares can get more complex. You can get into, and we'll learn some of these, where you get into multiple squares besides just 4. Sometimes you have multiple traits and not just one trait that's being isolated. So that's a really fascinating way to look at it. Now let's continue on. So in a genetic cross, what we're seeing here is the allele that each parent will pass on to its offspring is based on probability. We can know, if we know the genotype, for example, our guinea pigs here, if we know that the male guinea pig here is black and has the dominant traits of BB, and we know that the female is white, which means it's recessive and has the recessive traits BB, the female can only pass little b on to their offspring, and the male can only pass big B on to their offspring. So what that means is the only possible choices in this one, this would actually be the probability of having, if we had a purebred black guinea pig and a purebred white guinea pig, the only probability would be 100% chance of having black furred offspring. There's no chance of them having a white guinea pig offspring because the dad is passing dominant traits down to the offspring. Okay, so those 4 possible combinations exist and it depends upon the traits of the parents or the generations that are being crossed to know that. That brings us to one of our big objectives, which is, okay, what's a phenotype, what's a genotype? I've talked about it, I've used this terminology already for you. It's real simple. An organism's phenotype, okay, we're talking about its physical appearance, its visible traits, okay? Your eye color. What color your eyes are is your visible physical appearance. That's your phenotype. An organism's genotype is its genetic makeup. It's the allele combinations. So in the case of this example below, okay, we have smooth pods here. Here's a smooth pod that's big S, or big S, little s. And then we have dimpled pods, right? Okay, pinched pods. Those are little s, little s. These right here, the little s, big S, big S, little s, those are the genotype. The phenotype is what we actually see expressed, the smooth pods or the pinched pods. Okay, so phenotype was what we can see, it's physical appearance. Genotype is what's the allele combinations that are happening in organisms. One other thing to notice is the difference here, we talked about these two, the difference between a homozygous and a heterozygous organism, okay, or homozygous and heterozygous traits. Homozygous traits is when an organism has 2 identical alleles for a trait. So in these examples, which ones would be homozygous? Well, if you think about it, which ones have identical? Well, this is homozygous and this is homozygous. So smooth pods, that's a purebred homozygous. Pinched pods, that's a purebred homozygous. Heterozygous, and remember we've talked about these words before, homo means same, okay? Hetero means different. So if you know that the prefix to the word, you know that heterozygous organisms that have 2 different alleles for a trait. So this guy would be our heterozygous with the smooth pods because he has 2 different alleles. Okay, that's the difference between genotype, phenotype, and between homozygous, heterozygous. Now, this is a quick little activity. You don't need to write this one down. I just wanted to go walk through this one and take a look at this image. So here we have one of Mendel's crosses. He's looking at he's got number of plants and the phenotype of their offspring. You'll notice through these crosses, he allowed several F1 or second generation pea plants with yellow seeds to self-pollinate. So the graph shows the approximate number of the offspring with yellow seeds and with green seeds. Okay, how many do we have with yellow seeds? Well, we notice that there are 6,000 yellow seeds that were propagated and 2,000 plants that had green seeds. Okay, we see that. Then what I want you to do is look at the information. Let's calculate the total number of offspring that resulted from this cross. That way we can calculate the percentage of the offspring with yellow peas and with green peas. So 6,000 plus 2,000 would give us a total of 8,000 total plants. And we notice we can look at each one. The first one would be yellow pea seeds, which would be 6,000 divided by 8,000. Okay, 6,000 divided by 8,000 would be the same as 6 over 8, and 6 over 8 would actually equal 0.75, or that would be 3/4, right? Which would be 75%. Okay, because 6 over 8 equals 3/4. And if you think of a pie, if I color in 3/4 of the pie, how much of the pie is actually colored in? 75%. And the cool thing is, now that I know that, I can also know the green seeds. Well, what's left over? If I use 75%, then that means that the green seeds made up the remainder, 25%. So there are 8,000 total plants he looked at. 75% had yellow seeds and 25% had green peas. Now, use the answers to question 2 to infer the probable genotypes of the parent plants. So what we're going to do is take a look at a possible Punnett square. So if we draw a Punnett square down here in our notes, Remember, we draw a square, divide our lines. What are the possible, what are the possible genotypes of the parent plants? Well, we can think about it. What do we have? We have green seed, which is obviously we're dealing with a recessive gene. So we can do, let's just say we'll use B. So little b, okay, which means we've got a B down here and a B over here. And we have yellow seeds, which could be either, those are dominant, so they're going to have a big B, right? So I know I have at least a big B in each one. Oh no. Which tells me what? Well, can this big B come from here? Nope, so it has to come from over here because 75% had that trait expressed. So that means this has to be this. And that tells me as well that this one's here, right? Because this has to be this. And so what we end up getting is that our Punnett square would realize that we both would have the genotype probably of big B, little b. Last thing we're going to talk about is codominance. And codominance is just a term because, see, we've kind of missed something in this process. What can happen in genetics? So we do all this information talking about alleles and crosses and Punnett squares and all this stuff, and we get it together and we think, oh, wow, this is so simple. Genetics, all I do is find out the genotypes of my parents, put them in a Punnett square, and I know exactly what my traits are. The problem is not all the alleles have what we call simple dominance. In some things, like codominance or multiple gene inheritance, you're going to get a place where it's going to be a little different. In codominance, the alleles are neither dominant nor recessive. Okay? They're not both. In that case, so what happens, both alleles express themselves in the offspring. And so you take, for example, these chickens here, okay, these rooster chickens. If these are both, now notice what they used here. Here's the male. The male is FBFB, okay? Notice neither of them are dominant. They're both large, but see, look, what do we have here? FWFW. So B is expressing a trait that is observable, and so is W. Since they're both expressing neither of them, right? Neither of them can be dominant. So instead of being dominant, they'll actually get a blend or a mixture, okay? And so what their offspring looks like is instead of being a white chicken or a black chicken, they're black and white. This is codominance. This is where both alleles are expressed in the offspring. And this happens in different types of organisms. It's not completely uncommon, okay? So that's just a quick introduction or a little bit more information into Punnett squares and probability and codominance. Hopefully you have a good grasp of genotypes and phenotypes and things like that. And we're going to keep moving on and keep learning about genetics. So thanks so much. Talk to you later. Bye.